So it needs molecules to collide. It needs to collide with sufficient energy. The correct orientation.
Very good. That's it, right? So what particle collision theory states, right, is that a successful collision where reactant bonds are broken to form products occur under two specific conditions that need to be met. And the first one is we need an energy that's greater than the activation energy. The activation energy is the minimum energy to break reactant bonds. So that makes sense, right? And the second thing is you want the particles to collide in such a way that the bonds are exposed and they break upon collision. So you need the correct orientation. And it's the second one that students often miss. Now, in Year 12, we don't really care about whether you say 1, 2, or both, right? What we care about is, can you link LCP with particle collision theory? So, Sid, how would you define the Chatelier's principle? What is LCP?
So when an equilibrium system is exposed to a change in conditions, it will shift to partially counteract that change. So whatever happens to it, it will do the opposite.
Very good. You're doing really good at explaining. I like that. Because when you explain and teach something, you understand it, right? The only thing I'd add, Sid, is dynamic equilibrium, right? Because LCP does not apply for static equilibriums. Good. So a system in dynamic equilibrium, when subject to a disturbance, will partially counteract that change. Now, Rithanya, can you remind the class what happens to reaction rate? What happens to concentrations at equilibrium? What can we say?
The forward and reverse reaction rate is equal.
Good. So that is the definition of equilibrium, right? For something to be in equilibrium, the forward reaction rate needs to equal to the reverse reaction rate. So when they're greater than 0, that's the dynamic equilibrium. When they're equal to 0, aka when a forward reaction has gone to completion and stopped, then we have a static equilibrium, right? So Nikita, what are the factors that affect equilibriums?
Concentration.
Yep.
Temperature.
Good.
And for gases, it's volume and pressure.
Very good, right? So those are the 3 key factors that affect LCP. Now, actually, what are the 4 factors that affect particle collision theory?
Wait, are you asking me again?
Oh no, Akshita.
Oh, sorry.
So for particle collision theory, was it the concentration?
Good.
The temperature?
Good.
The pressure and volume?
Not quite, because pressure is concentration, but just for gaseous systems, right? So yeah. You're kind of right in saying pressure volume. I'll give you that, but there's 2 more linked together. And you want to give it a go. Why do we have to crush up tablets when giving it to patients, when giving it, IV, or if we want greater absorption? Why is that more important? Surface area, right? And what's the other last feature? This does not affect the equilibrium, but it increases the rate of reaction by decreasing the activation energy. What am I talking about, everyone?
Catalyst.
Very good. So a catalyst, right? So as you can see, there are a bit of similarities, a bit of differences. But Sid, can you remind us, how does particle collision theory link to the Chatelier's principle?
So however, like the conditions affect the dynamic equilibrium, say it was concentration, it will either increase or decrease the amount of collisions, which will then affect the rate of the forward and reverse reaction. Whichever is like greater, that side is favored, and it shifts that side.
Very, very good, right? So I'm very happy with that explanation. So everyone who is listening, in summary, the Chatelier's principle is a prediction system, right? You never understand why it's partially counteracting change. You just have to justify the system wants to counteract change. The why as to why LCP happens is particle collision theory, right? So as Sid mentions, when you change concentration, temperature, or pressure volume, you're changing the forward successful collision rate and the reverse successful collision rate. One will be favored, and that's the direction the reaction proceeds. When you take a step back, it looks as if the reaction is partially counteracting changes, when in reality, all it's doing is it's changing its successful collision rate. Okay, very good. So that's where we left off upon. So I did show you all a few questions, but I think now I'm happy for us to move on. I'll just give you one question about particle collision theory and LCP, just to make sure you'll understand it very well, and then we'll jump straight into the next part of our content, which should be our graphs, which I really like, because the graphs are super high yield towards your Mod 5 exams. I would say concentration time graphs, quantitative equilibrium, you'll soon learn about the K constant, are the two most central elements of Mod 5 from an exam point of view. Okay, so maybe we'll do one quick question about, maybe not temperature, but maybe we'll do, here's your question, right? So I want you to imagine that we have this reaction here. And I love to give you this reaction because it links to Module 8. It's one of the most important reactions in Chem. I'm sure you all know by now this is the Haber process, right? So everything is gaseous. Anyone remember the enthalpy? I've asked it a couple of times, so maybe it's stuck. Okay, so it's exothermic, right? So I want you to explain using particle collision theory why increasing the concentration of nitrogen will cause the equilibrium to shift to the right-hand side. And I don't want a written answer. I'm going to just ask you on the spot because you need to get to the point where you can teach and explain it from the top of your head. So, Nikita, any ideas why increasing nitrogen concentration would shift the equilibrium to the right? Not according to LCP, because I'm sure you all know by now, increasing nitrogen concentration, the system wants to counteract that. It'll want to decrease nitrogen concentration. It will shift it to the right-hand side to do so. But can you explain it using particle collision theory, Nikita?
Yeah. So when there is an increase in concentration, the particles collide more often, and basically there's a higher yield, and because
very good. Now I'm going to help you answer that in an exam point of view, right? So you're completely right. There's an increase in the number of collisions, and yield is just the amount of product that you produce in a reaction. So for everyone else, exam-wise, the way I'd articulate that is when you increase the number of nitrogen particles, you increase the number of total collisions of nitrogen, and you also increase the number of successful reactant collisions. Okay, because let's say 20% of all collisions are successful. If my collisions per second go from 100 per second to 200 per second, my successful collisions then go from 50, if there's a 50% success rate, to 100. So now I have a greater rate of successful collisions, which means my forward reaction rate has increased. But what's happened to my reverse reaction rate? There's been no change. So as Sid mentioned, it affects both reaction rates. And so what does it look like when the forward reaction rate is increased? The reverse reaction rate is immediately the same at time equals 0 at the initial phase. What direction, actually, does it look like the equilibrium is shifting? So, Akshita, my forward reaction rate has been increased.
Was it the left side?
Think about this. If my forward reaction rate has increased, what is a forward reaction rate, Akshita? What is colliding to form what?
Nitrogen and hydrogen.
Yes, to form what?
To form ammonia.
So what's happening to the concentration of ammonia?
It's going to increase.
What's happening to nitrogen and hydrogen?
It's going to decrease. Oh, yeah.
Right? If I give you, I don't know, 2 pieces of butter and 3 eggs to make cake, the butter and cake disappear and more cake forms. It's a very similar point even in reactions. You use up reactants to form products. That's super important, right? So this, when we say an equilibrium shifts to the right, everyone, we're not saying the forward reaction is greater than the reverse reaction all the time, because to have an equilibrium, they need to be equal. When an equilibrium has shifted to the right, what that means is now there is a greater constant concentration of product and there is a smaller constant concentration of reactants. Does that make sense? So temporarily, we form more ammonia and then that concentration increases and it stays at a high value. And at the same time, the nitrogen and hydrogen concentration drops down as the forward reaction rate increases temporarily. And when it reestablishes equilibrium, it stays at a low constant concentration. Does that make sense, Akshita?
Yeah.
Good. All right. So important to understand when you say something shifts to the right to know what it means. That's how we explain it, shifting to the right-hand side. Very good. All right. I think we're good to move on. The one thing I would say, guys, is the examiners in your trials in HSC know students struggle linking collision theory to LCP, especially with temperature questions. So get very familiar with it. When you go to the past HSC papers, you'll see a lot of questions relating to these graphs and equilibrium, collision theory, and temperature. So do as many as you can. Good. All right, did anyone hear about, just a bit of a segue, did anyone hear about the 2022 HSC Chemistry paper? They started on Monday. Good. Rithania, what did your friends in the year above say?
They said it wasn't that bad, but they struggled in, I think, one of the long response questions.
Yeah. So that's the general gist I got. So from my students who've got back to me, they've mentioned that the HSC Chem exam was quite easy, straightforward. But there's one question. When we get the paper, I'll show you all what the exams look like, right? So you get comfortable with knowing what level of information do I need to know? Is it calculation heavy? Is it concept heavy? Is it experimental heavy, right? Good. Now, this part is, I think it's honestly very fun because there's not really too much explanation per se, but it's understanding what's going on in these graphs. So concentration time graphs, let's briefly talk about them. When a system is in equilibrium, Jacob, what do we say about the concentration of all substances? Are they equal? Are they constant? Are they changing in a dynamic equilibrium?
It's constant.
Very good. So, Jacob, you can see here from time equals 0 to time equals t, you see gas X, gas Y, gas Z, right? What can you tell me about that system? Is it in equilibrium or not between time 0 and t?
Yeah, it's equilibrium between 0 and t.
Very good, right? Now, the only thing, the difficulty here, everyone, as you can kind of surmise already, is we don't know who the reactants are, we don't know who the products are. And if you look down to the question, you can see the question is testing you on exactly that. Whether you can find out who are the reactants and who are the products. Now, whenever you're analyzing a concentration time graph, I want you all to remember this. There are 2 parts to the concentration time graph, right? Whenever we make a disturbance, there are 2 phases of change. And a disturbance was made at time equals to t. And if you read the question, it should tell you the disturbance. Change was imposed at time equals t, equilibrium was reestablished. Okay, so we don't know the change, but I'll help you all out with that. Okay. So again, there was a disturbance at time equals to t. And then you can see the gases suddenly change at this point in time. I'm going to highlight it. At this point in time, all the gases suddenly change. And then what happens is there is a gradual second component of change. Can you all appreciate that? There is an initial change, and then there is a gradual change that takes place until this dotted line that I'm showing you here. Now we're talking about dynamic equilibrium, right? So, Rithania, what are the 3 disturbances? Nikita mentioned this earlier. What are the 3 disturbances you can impose on a system that was happily in dynamic equilibrium until time equals t?
Temperature, concentration, and pressure and volume.
Very good. Pressure, volume, right? Now, since these are three gases, Tanya, does pressure, volume apply or not?
It does.
Very good, right? So all three are on the charts here. Now, I want you guys to think about this. Which one would affect all three gases immediately? Can you see this sharp change where all the gases dropped in concentration? Do you think changing the concentration of one gas would cause such a drastic immediate change to all three gases, everyone? Sid, what do you think? Do you think concentration could give you this pattern of change?
I think it might have been pressure that would have affected.
Right? Good. So I think that's very reasonable, right? Because when you change the volume of a vessel, the pressure, which is the concentration of a gas, that's what pressure is, right? Concentration of a gas and the force it exerts on the wall of a vessel, it all rapidly changes. Now, what we can appreciate here is immediately the concentration of all gases dropped. Or we can say the pressure of the vessel dropped. How can we make pressure drop? What do we need to do to volume? Jacob?
Increase the volume.
Good, right? So I'm thinking likely the imposed change based on this pattern that all three gases were affected at time equals 0 must be pressure as a disturbance. Okay, now I want us to pause this question because we will go through the rest of this question very shortly. But I just want you to highlight and appreciate this is exactly what a pressure volume disturbance on a vessel looks like. There'll be a sharp, rapid change for all three substances, and then they will gradually return back to a constant concentration, which is what equilibrium is. Now, let me just briefly show you what a temperature disturbance looks like, right? So, T2. Nikita? What do you think the disturbance was? So as we mentioned, disturbances can be pressure, volume, concentration, or temperature. Nikita, does this look like the previous graph where there's a sudden change in concentration of all the gases and then a gradual change after that?
Yeah,
Good.
they're all increased.
Very good. So you can reasonably say this stimulus at T2 or this disturbance was likely an increase in pressure or a decrease in volume of the vessel. But now, everyone, I want you all to have a look at T1. Right? Remember I told you there are always two phases of disturbance. There is that initial phase, and then there is a gradual adjustment phase after that. So you'll always see this adjustment phase. Do you see how there's an adjustment phase here? There's an adjustment phase here. But what do you all notice about that initial phase, that stimulus phase that I've highlighted in yellow? Did all the gas concentrations change in that yellow phase? Sid, we'll go to you. Or did only one gas concentration change in that yellow stimulus phase I've shown you at T1?
Only nitrogen gas shows an increase.
Very good. So from that, Sid, you can reasonably conclude what must the disturbance be if only one of the gases increased in concentration?
Then it would have favored the forward reaction.
As in, what was the disturbance? Don't worry about the direction.
The addition of nitrogen, the increase of concentration, yeah.
Very good, right? So now you're all starting to learn how to pick up what the disturbance is, which is the first part of this reading concentration time graph game, right? What was the disturbance? If the concentration of only one substance increases in that initial phase, the disturbance is concentration. If the concentration of all three substances increases in that initial stimulus phase, the disturbance was pressure or volume. And finally, have a look at this stimulus phase, everyone. T3. Guys, at T3, do we see a change in any of the gas concentrations immediately in that initial stimulus phase? Rithanya, I'll go to you. At T3, at that yellow vertical line that I've shown you, do you see a sharp change in concentration of any of the gases?
No.
No. What you see instead is only the second phase of change which I showed you, which is the counteraction phase. This is very characteristic of temperature. Because as you all know, when you change temperature of a system, immediately, the second you change temperature, nothing happens. The second you increase temperature, all particles have increased kinetic energy, but you need time for the particles to collide and change from reactant to product. Does everyone agree? And so what you end up seeing is this gradual change in concentration only later in time. So in summary, there are two phases of change in a concentration time graph, right? The initial yellow lines that I've shown you, those are the initial or stimulus phase, which I like to refer to. That will tell you what the disturbance is. If all three go up, Nikita, what must the disturbance be?
Pressure or volume.
Very good. And Rithanya, if only one substance goes up or down, what must the disturbance be?
Concentration.
Good. And actually, if nothing changes in that initial stimulus phase, what must the disturbance be?
Temperature.
Very good. Right? And there will always be that second counteraction phase where everything changes gradually. In fact, that second counteraction that phase, the blue lines that you can see that I've shaded and shown you, that's what Le Chatelier's principle is predicting the system will do, and the system is doing that in exactly that manner. Okay, so again, stimulus phase, yellow, counteraction phase, which I've shown you in blue, is the phase that follows stimulus phase. This tells you the disturbance. That's the first phase. And the second phase, which is a counteraction phase, that changes according to LCP. Good. So with this newfound knowledge, let's go back to this graph here, this question. This is from your HSC additional question booklet. It's free. It's for every single student in New South Wales to use. Those of you who haven't seen this before, just search NESA HSC Chem additional questions. It's a 90-page document full of beginner HSC questions for you to do. Okay, let's have a look at this, right? I'm going to rub out all my smiley faces and this stuff. So I'm going to give you all about a minute or so to come to an answer, and hit the raise hand icon once you've come to an answer. I don't care if you're right or wrong. I just want you to put you in an uncomfortable position where you haven't seen this question type before, and I want to see how good we are at working ourselves out of tight situations. There'll always be a question in your HSC Chem exam which will put you off, just like some of the students have mentioned for this year. So I want you guys to get prepared answering partly application questions. Good. Rithanya, have you got an answer or do you have a question?
Answer.
Oh, good. Very good. I'll wait till about 3 of us have got an answer and then I'll ask. Good. Said. For one more person to get to an answer and then I will break it down for us. Good. Nikita. All right. Okay, Jacob, I'll get you to break this graph down for us. So again, Jacob, what were the two phases of change in a concentration time graph?
Wait, sorry, what was that?
What were the two phases of change in a concentration time graph?
So just like the change which is opposed onto the reaction.
Yeah.
So the stimulus.
Good. And then
the concentration.
Well, the counteraction phase. That's what
yeah.
Break it down, right? Now these are words that I use, right? You don't have to refer to it like this in your exams. It's just for you to understand what's going on here. So there's an initial stimulus phase, right, which is the disturbance we've imposed. Now we've done this enough, and what do you think the stimulus is? We've already gone through this, but just remind us.
Pressure or volume.
Good. Pressure or volume. Now specifically, and remember, whenever you're answering those 3 questions I told you, what is the stimulus? What is the opposite? And what is the direction? Those are the 3 questions we always ask ourselves, and we can always answer LCP questions like this. With a stimulus, you have to be very, very accurate and precise. So, Anne, was it an increase in pressure or a decrease in pressure?
A decrease?
Good, a decrease in pressure. Very good, right? So it's been a decrease in pressure. Now, and according to the Shadley's principle, what is the opposite of decreasing pressure?
Increasing it?
Good. So which direction would the system want to go? Would it want to go to the direction that makes more gas moles, or would it want to go to the direction that makes less gas moles?
The one that makes more gas moles?
Good. So therefore, we want to go to the side that produces more gas moles. And we have no idea what direction it's gone yet, because we don't know who the reactants are, we don't know who the products are. Now, this next point I haven't taught you yet, but I wanted to see if anyone could pick this up, right? Now, what did I say? The next phase is that counteraction phase, and it obeys Le Chatelier's principle, this change that you can all observe here. Now, have a look at the degree of change, everyone. Now, let's say this changes by x units, right? Or in fact, you have the graph. So this is 0.8, this is 0.9. So this is 0.005, 0.005 change, right? So this was a decrease of 0.005. What happened to the other gases? So Nikita, what happened to Y and Z? Did they increase or decrease, and by how much?
They increased by
Good.
like 0.005 each.
Good. Right? Now, everyone, the sign tells you which side the gases are on. Right? So since X decreased, Y and Z increased. It's telling you Y and Z belong on the same side of the reaction, and X, which decreased, belonged on the opposite side. So what's happened here is we've gone from the side of X and used X up, exactly 0.005 moles per liter, to produce 0.005 moles per liter of Y and Z. Right? So straight away what you can do is you can go back down to these options and you can cancel out the options that don't have X and Y on the same side of the graph. Which one of these options, Sid, do not have X and Y on the same side? Sorry, not X and Y and Z on the same side of the graph.
A.
Good. Any others that don't have Y and Z? No, all of them have Y and Z on the same side of the graph. Very good. And the next thing is the ratio. What is the ratio of all of these gases, right? Now, this is the most important part of these concentration time graph questions to get a band 6. It's that the change corresponds to the stoichiometric ratio. Not the initial. Do you guys see how this decreased by this much, this decreased by like half of that, this decreased by less? That means nothing. It's the counteraction phase that I told you. This phase that obeys LCP, right? And it's the change in that phase that obeys the stoichiometric ratio, right? So did you see how all of the gases changed by exactly 0.005 moles per liter, everyone? That's telling you all of them have the exact same number in front of them in our stoichiometric ratio. So straight away, Jacob, what options can we cancel out?
You can cancel out B and C.
Very good. Now, Jacob, I want you to just confirm that this makes sense, right? So apply the whole stimulus, opposite, direction little template that we always use in answering LCP questions. So we said the stimulus is a decrease in pressure. We want to increase pressure, and therefore, as Ritania mentioned, we want to produce more gas moles. Now, what you can appreciate in this graph is we've decreased X and we've made more Y and Z. So which direction did we go, since option D is our answer, Jacob? Did we go to the left or to the right?
To the right.
Good. And is that the direction that has more gas moles?
Yep.
Good. It's got 2 gas moles on the right hand, 1 gas mole of Y, 1 gas mole of Z. We've got half of that on the left hand. So we have gone to the direction that produces more gas moles, and we have gone to the right hand side. So it all checks out. So our answer is D for this question, right? Now, I threw you all in the deep end here, right? And what I mean by that is there are simpler concentration time graph questions. They usually don't ask you what the ratio of the graph is, right? But I just wanted to see how you'd all do in those questions. Now, I want you all to do question 2. I'm going to rub all of this out for you. I want you all to just explain what the disturbance was, very briefly. Don't need a full answer. And remember, you're all getting these printed notes to you. It should come early next week. But I want you to just very briefly identify the change and explain the counteraction phase too. So why did ammonia increase? Why did hydrogen decrease? Why did nitrogen decrease as well? Right? So I'm just going to ask 3 of you at random to explain the changes that occurred at T1, T2, and T3. So when you guys have done this, very briefly, you can just write literally 3 points paper and be ready to answer this question. What was the disturbance at each of those times? And why does the graph appear so in the counteraction phase as well? Which direction did the equilibrium shift? That's what I want to know. Okay. Good. Okay, hit the raise hand icon once you've got an answer. So you can get some water. Okay, so let me get Rithania. Tell me what the change at T1 was and why the graph looks so after T1.
I think T1, there was an increase of concentration in nitrogen.
Good. And why does the graph look as such?
Because you increase the nitrogen, there's more ammonia forming.
So the first thing I want you all to do, and this is the reason this question is a little bit hard if you don't do it, is write the chemical equation. In all chemistry questions, I don't care if it's a conceptual question or a calculation question, if you don't write the equation, you will struggle to answer the question, right? So all of you should very quickly just spend 2 seconds writing the equation down, and that would make a lot more sense, right? Now you can apply the 3-question prompt that we've been working on for answering LCP questions. So Sid, why do we observe this change after an increase in nitrogen concentration?
So when you increase the nitrogen concentration, the equilibrium wants to lessen the concentration of that, so it shifts to the right and produces more ammonia. And because you're also reacting with hydrogen, that concentration goes down.
Very good. Very good, right? And let me ask you all an additional question. This graph doesn't actually capture the changes too well, but let's say that the concentration of ammonia increased by 0.9 moles per liter. What would you expect the concentration of hydrogen to change by and the concentration of nitrogen to change by? So what I've said again is that the change in concentration from that point to that point is 0.9 moles per liter. Jacob, what would you expect the concentration of nitrogen and hydrogen to change by?
Yeah, so nitrogen would change by, well, it would be 0.45, and then hydrogen would be 1.32.
Good. Yes. 1.32 or 1.35? Jacob, what would hydrogen change by?
Yeah, 1.35, that's what I meant.
1.35. Good. Okay. So for everyone who's wondering how Jacob got those numbers, and I'm sure some of you would have also understood this, is I told you that the change in concentration in that counteraction phase abides by the stoichiometric ratio. So ammonia has two parts in our cooking recipe or our stoichiometric equation, right? So the SR ratio, stoichiometric ratio, is a 2 in front of ammonia. Now, 2 parts is represented by a change in concentration of 0.9. So 1 part in our cooking recipe or chemical reaction is represented by a change in 0.545 moles per liter. And so we understand that nitrogen has a 1 in front of it, so nitrogen will change by exactly 1 part, which is 0.45 moles per liter. Hydrogen will change by 3 parts, so 3 times 0.45 moles per liter. It will change by 1.35 moles per liter. Now, this is a very common exam question they'll test you on, because a lot of students still can't appreciate that the change in concentration in a counteraction phase abides by the stoichiometric ratio, not the change in this initial stimulus phase. That has to do with nothing. It just has to do with what the disturbance was. Does that make sense to everyone? Right? So this decrease.
Wait, can you repeat that?
Yeah, sure. Let me just. I think I should rub this mess part out, and we'll go through the change in concentration again, right? So what is a stoichiometric ratio? The stoichiometric ratio, the reason I call it a cooking recipe is because it tells you how many parts of your ingredients you need to make how many parts of your final product. We need 1 part of nitrogen per 3 parts of hydrogen to make 2 parts of product or ammonia. Does that make sense to everyone? Right? Now, remember, there are 2 phases in a concentration time graph when you make a disturbance. Nikita, what are those 2 phases?
The partial change and then the LCP.
Good. So the initial change or the stimulus phase, and then the counteraction phase, which abides by Le Chatelier's principle. Right? Now, the question I gave you all was, I said the nitrogen, which is this dotted line, has increased by 0.9 moles per liter. And I asked you all, how would the concentration of hydrogen and nitrogen change? Right, Nikita, what number is in front of ammonia in our stoichiometric ratio?
2.
2, right? So I know a change of 2 parts is represented by 0.9 moles per liter. So how much would a change by 1 part be represented by?
0.45 moles.
Exactly, right? So I know a change of 1 part is 0.45 moles. And Anne, how many parts does a nitrogen change by?
By 1.
1, right? So we know, well, nitrogen is a change in 1 part, so it must change by 0.45 moles per liter. And did nitrogen increase or decrease looking at the graph?
Nitrogen decreased.
Exactly, nitrogen decreased. So we just put a negative sign there. Same thing with hydrogen, right? Hydrogen changes by 3 parts. We do 3 times 0.45, and you'll get the change in hydrogen is 1.35 moles per liter. Now, does hydrogen increase or decrease, Akshita? Hydrogen in this question.
Decrease.
Exactly, right? So then just put a negative in front of it. So it decreases by 1.35 moles. Does that make sense to everyone? Nikita, does that make sense?
Yeah.
Good.
But wait, I have a question. So what if they haven't given you like that change? Like they haven't said plus 0.9. Then can you just guess?
If they didn't give you that change, first of all, you wouldn't have to answer that question. But if you were required to draw it, for example, you would have to show everything in proportion. So that's something this graph is not doing too well. Can everyone appreciate that? Everything is changing from what I can see by more or less, or maybe the graph has done it in proportion. So if you got a ruler and you measured this as x, and you got a ruler and you measured this, and you got a ruler and you measured this, they should all be changing by the stoichiometric ratio proportions, right? I cannot tell you if they have because I'm annotating on my iPad. I can't measure it. But let me show you a question where you have to draw a concentration time graph. And here is your perfect example. This is a 2019 HSC question 25. They've asked you to sketch the concentration of the remaining gases now. And so now this is where you have to really think, am I abiding by the stoichiometric ratio in that counteraction phase? And am I representing the initial phase fairly? So what I want you all to do is you can either choose to quickly open the 2019 HSC paper and print this one page out to do, or you can very quickly just draw it out in your booklet, whatever you prefer. But by next lesson, you'll have the booklet with you, so you can just write directly on it, okay? Just for this lesson, pick what you'd like to do. I would just probably just draw it out and get the general ratios. Sid, question?
How, like, you know how you said it changes by 0.9 moles per liter?
Yep.
Can you calculate that quantity, or can you?
Can you calculate? No, you can't, because it really depends on the stimulus, right? So there's no way to calculate it until I teach you the K constant and quantitative equilibrium. Once I teach you that, Sid, so once you go through the second inquiry question for this module, you can start to calculate it, yes.
Yeah.
Good question. Yeah, so I made it up in that scenario. It might not be right, etc. Good. All right, I'm going to give you 30 seconds to just get started on this. So guys, just feel free to just write it however you like. Your graphs will look slightly different based on how you draw it in your book, but just use a ruler, please, so you can get used to drawing it correctly. Okay, Britannia, what are the 3 questions you always ask yourself with LCP? Because whenever I'm doing an LCP question, I very quickly jot down those 3 questions. What were they again?
Stimulus, opposite direction.
Good. What's the stimulus for this question?
The decrease in concentration of CO.
Very good. I like how we're being very specific with our stimulus. What's the opposite of that, Akshita? Opposite of the stimulus. You got the easiest question.
The increase of concentration of CO.
There you go. Right? And then finally, what direction do we want to go? So you need to ask yourself, what direction does my arrow have to point to increase CO? So if I want to increase CO, I just point my arrow at CO. Wherever the arrow tip points is a direction where everything will increase, right? It's going to shift to the left-hand side. Very good. So let's start with the initial stimulus phase, because we always break it down the same way. Should the concentration of any of the other gases change in that stimulus phase? Jacob?
Do you mean like an abrupt change where it's like straight
Yes,
vertical?
exactly.
Oh, no.
No, exactly. So when I'm talking about stimulus phase, I'm talking about at that exact point in time, should there be any change, so vertical change in the concentration. So forget about any time after that. So exactly that. So Jacob's completely right. There's going to be no change in the concentration of any of the other gases, right? Sid, in what type of disturbance would you see a change in concentration of all the gases?
Pressure and or volume.
Very good, right? And we don't have that in this case. So now we'll move on to the counteraction phase. These are the things you need to be careful of when you're drawing a concentration time graph. Drawing a concentration time graph is much harder than just interpreting one. You're all quite good at interpreting concentration time graphs. When drawing it, this is what I like to do, right? The first thing the marker is looking for is, do you see exactly that point where the concentration of carbon monoxide stabilized? right? There is no further change in concentration over time. It's at that point in time, T2, where everything needs to reach a constant concentration, aka it's at equilibrium. Is everyone with me? Right? So if any of your gases are still changing concentration going up or down after T2, your graph is immediately incorrect. The next thing I'm looking for is, are you abiding by the stoichiometric ratio? So the two things I'm looking out for is, number one, are they all equilibrating at the same time? Same time of equilibrium. Second thing I'm looking for is, are you abiding by the stoichiometric ratio? And these are the two checkpoints you need to have in your head when you're drawing these graphs, right? So my horizontal line is quite wonky, so I'm neating it up for us. So zooming in. Good, right? Okay, so how many units? Don't worry about, there's no numbers here, right? So just tell me, so let's say this is 0.1. How many units did carbon monoxide increase by? Akshita, how many units can you count?
0.3.
Exactly, right? So there's been an increase in carbon monoxide by 0.3. And what did we say? We shifted to the left-hand side. So everything on the left-hand side, depending on how many parts there are, will decrease or increase by that same ratio. Now, luckily, everything is 1 here. In your trial exams, they won't be this nice on you. There'll be a 2 here, there'll be a 4 here, and we'll do a question as if it was like that as well. But since everything has a stoichiometric ratio of 1, Britannia, what will the change in concentration of every single substance be? By how many units?
Are you asking in terms of the 0.3 or?
Yes, in terms of 0.3.
Everything would be 0.3.
Exactly, right? However, okay, so Britannia, what will happen to water?
It would decrease.
Think about this. So the stimulus phase is what happened at that time. Everything from that time to T2 will obey this direction phase. Which direction did we go, Britannia?
Left.
Left-hand side, according to our stimulus opposite direction template, right? So everything on the left-hand side will increase. Everything on the right-hand side will decrease. Does that make sense to everyone? So between T and T2, that is what's going to happen. So we can appreciate that carbon monoxide increased after the stimulus phase. So in this change, it increased. So what would happen to water similarly, Ratanya?
It will increase.
Yeah, so what I would do is I'd zoom in here. I'd go, well, exactly how many units is 0.3 above? It's right there. And I need to get there. I need to stabilize my graph at that point in time, right? So what I'll do is I'll increase it like this, and it'll stabilize at that point in time. So that's what my graph will look like. Okay, 1, 2, 3. Now, what about hydrogen and carbon dioxide? Nikita, what will happen to hydrogen and carbon dioxide in this concentration time graph?
They'll both decrease by 0.3.
Very good, right? So all I need to do now.
Also, I have a question.
Yep.
What's the SOD thing, and then what's the D, like the 2HS?
Good question. So SOD is a little acronym I use to answer every single LCP question, and I've trialed it over the last 7 years, and there's not been a single LCP question you cannot answer when you follow this template. And the template is literally, what is the stimulus out of the 3 factors you've spoken about? You have to be very specific with it. Is it concentration, temperature, pressure, volume, and is it going up or down? Opposite is the O, and you just literally write the stimulus but put the opposite direction arrow. And then direction is, are we going to the left-hand side and right-hand side in order to achieve that opposite? Does that make sense?
Yeah, okay.
Yeah, so as you do more and more questions, it'll make much more sense to you. Good. So going back to hydrogen, we said that hydrogen and carbon dioxide will decrease by 0.3, right? So carbon dioxide decreases to this value. And I'll just show a line that decreasing like this. And then we can show our hydrogen decreasing by the same. decreasing by this amount, like this. There you go. If you do a graph like this, you would have got 4 marks for this question. Good. All right, question 25B. I'm just going to ask one person in about 30 seconds to verbally explain it. So just verbally prepare your answer plan. Don't worry about writing anything. You can write it once you get your booklets. Jot down maybe a few buzzwords that you'd want to use in explaining this to me. Once you're ready, just hit the raise hand icon. Okay. I asked the previous class this. Does anyone know how to code in this class? Anything. It could be Python, JavaScript, C. Anyone learned any coding? Sid?
Yeah,
Jacob?
sort of.
Nice, nice. Did you teach yourself or did you learn it at school?
I did software at school.
Very nice, very nice. I wish I had a software class when I was back at school. But like I was telling the earlier biology class guys, a really important skill, I want you all to at least try, see whether you like it. If you don't like it, don't force yourself. But if you do like it, amazing. Because with any kind of business startup that you want to work on, whether it be in healthcare, when you're a doctor, or whether it be in engineering, if Sid's working on electrical, civil engineering with, I don't know, building a Tesla kind of vehicle, you need to understand software and code, right? It could also help you a ton in artificial intelligence, etc. Just to give you a little example, two of my friends recently started a startup company in healthcare where they created an artificial intelligence that acts like a patient, and medical students can ask the artificial intelligence questions and it will answer back with a medical history. And those two students, just because they were in medicine and they knew how to code, had the unique opportunity to create that startup. And now NSW Medicine, UCID Medicine, medical schools in the US are using that technology, and that startup has blown in size, proportion, annual revenue, etc. And it's really cool to see that if you have unique skills, you're at the top 20% of everyone else at 2 or 3 different things, you can combine them and you'll create new opportunities for yourself that you would have never otherwise had. So school does not tell you to do these things. So I'm going to tell you things like investing, things like learning how to code. I would highly encourage you to try just exposing yourself to that now. So by the time you're my age, you're really good at those things. Good. Coming back to this, Anne, could I get you to answer 25B for us?
Yeah, so I said with a decrease in carbon or CO, there will be a decrease in reactant molecules, which means there'll be a decrease in reactant collisions. So then a decrease in successful reactant collisions.
Good.
This reduces or decreases the forward reaction.
Good.
Leading to the reverse reaction being greater than the forward reaction.
Very good.
So then the reverse reaction will be favored, which will then lead to the concentration of CO and H2O gradually increasing to reestablish equilibrium.
Very good. Very good. So reactant concentrations will increase. Good. The only thing I'll mention is when you use the word successful collision, do try to define it. So very quickly write successful collision, bracket, reactant bonds broken. Something along those lines. Does that make sense? Because the examiner, especially when you say HC, they will not know what a successful collision definition is, or they'll want you to define that. They will know the definition, but you will need to define it. It's very one of the small things. It's kind of like the first time in your exam when you say LCP, you have to expand it with brackets saying Le Chatelier's principle. Otherwise, they have full right to take away a mark. And I know it's quite silly because they know what LCP is, you know what it is, but it's small exam formalities that you need to have. Good. I want you guys to answer, question set B. I'd like you to do question 9 and then D and II. We'll talk about what yield is very quickly. Guys, what does yield mean? So Nikita mentioned this at the beginning of this lesson, but it has a very formal name or definition. I'll give you a hint. In your Mod 5 exam, I test you on yield. So you will need to know what it is. Sid, what's yield?
How much of something is produced? So could I say it's the extent of the reaction, or?
Okay, you're very close. So you're completely right in that yield is the extent of production of a substance, but it's usually expressed in a particular way. It's expressed as a percentage, and it's usually divided by its theoretical maximum. So guys, what I mean by this is if I get 1 mole of nitrogen, actually I'm going to make it very easy for us, right? Let's say I get 2 moles of nitrogen and I react it with 1 mole of oxygen. What is the theoretical maximum number of moles of nitrogen dioxide I can produce? Britannia?
3.
Remember, what is stoichiometric ratio? It's telling you the parts in a cooking recipe in moles, right? So the stoichiometric ratio of 2 to 1 to 2 is telling you if you get 2 moles of nitrogen dioxide, you mix it with 1 mole of oxygen, how many moles of nitrogen, if I get 2 moles of nitrogen monoxide, I can combine it with 1 mole of oxygen. Britannia, how many moles of nitrogen dioxide will I make? What number's in front of it?
2.
2. The answer is 2, right? So 2 is a theoretical maximum amount of nitrogen dioxide I could produce if the reaction went to completion. But as you guys can see, the reaction does not go to completion. So then if I told you that 1.9 moles of nitrogen dioxide were made, the yield in this reaction is equal to 1.9, which is the actual amount produced, divided by 2, expressed as a percentage. Right? So you just times that by 100 to get the percentage. And that is the percentage yield of the reaction. Does that make sense to us? Yield is the amount of something produced divided by its theoretical maximum, expressed as a percentage. Good. Now, the reason I went through it in that much detail is they can ask you calculation questions about yield, and you'll be introduced to that very shortly. So I want you to just understand what the formula is to calculate percentage yield first. Good. But anyway, coming back to this, please hit the raise hand icon once you've got an answer. Once we've done these 2 questions, I'll let you take your break, and then we'll recap. As some of you might know, we are going 30 minutes over time today because last lesson we finished 30 minutes early. Okay, so that's that. So I want us to take maybe 2 breaks, so we're ready to answer these questions. Good. Nikita's got an answer. Jacob's got an answer. Wait a little bit longer.
Excuse me. I have another question. Why do they say partial change? Like, why do people say partial change?
Very good question. So I'm going to get one of your peers to answer that. And why does the Shadley's principle say partial change? And any ideas?
I'm not really sure how to word it, but like it's a partial change because if they were to make fully change it, then the other side would have the I'm not sure how to word it.
No, it's all right. It's a hard question to word. But first of all, let's talk about what partial change means, right? What partial change means is if I was to increase the concentration of carbon monoxide in this equilibrium by 1 mole per liter, the system will shift, counteract the change, but it will decrease the concentration of that carbon monoxide by 0.5 moles per liter. So the net effect is we went up by 1, we went down by 0.5. The net effect is we've still gone up by 0.5. Right, so that is what a partial change means. So the Chatelier's principle is telling you that when you increase the temperature of a system by 10 degrees, it'll drop it down by 8 degrees. If you increase concentration by 2 moles per liter, it'll drop it down by 1.5 moles per liter, right? Now, if you want to ask, well, why does it do that? There's a vague answer and a specific answer. The vague answer is, in nature, everything is partially counteracting change, right? Inside your body, we are partially counteracting changes in body temperature, in the pH of our blood, etc. If I drop your temperature by 2 degrees by putting you in a really cold room, you will shiver, you'll have goosebumps, but your temperature will not go back up by exactly 2 degrees. You'll still feel cold in a cold room, right? And then to give you the specific chemistry exam answer, it's because of particle collision theory, right? If you really think about particle collision theory, if I increase the concentration of carbon monoxide, I'll increase the number of collisions of carbon monoxide, and some carbon monoxide will get converted into product. But I'm not going to increase the number of successful collisions of carbon monoxide so much that I use up more than 1 mole of carbon monoxide. That doesn't make sense, because if you need to actually use little particle thought experiments and understand this, right? If I increase the number of carbon monoxide molecules by 4, those 4 carbon monoxide molecules will engage in successful collisions. They'll engage in collisions, but maybe only 3 of them will engage in successful collisions and form products. 1 will collide, but it won't be successful. And so the net effect is, I increase the concentration of carbon monoxide by 4. I drop down by 3. The net effect is there's still an increase of 1. So TLDR, the answer is particle collision theory. And broadly speaking, it's because that's how nature acts in various systems, in the body, in physics, even in chemistry. Does that answer your question, Nikita?
Yeah, thank you.
A long answer, but the reason it's long is because this is probably the one thing students stuff up most about Le Chatelier's principle. They don't understand it. It's a partial counteraction and why. Good. All right, so going back up, what's our answer for A? Question 9A. Sid, what did you pick?
Since it's exothermic, I would say to cool the system.
Actually, I mean 2001, question 9.
Oh, okay. D.
Okay, let me go to Jacob. Jacob, what do you think about question 9? I think this is a vague question. The understanding of LCP is important in the chemical industry, right? Which prediction can be made using this principle? Can LCP tell you the identity of products, Jacob?
What do you mean? Well, it can tell us like how we can increase the yield and stuff like that.
That's true, but will it tell you the identity? Meaning, will it tell you there's ammonia in a mixture? They'll tell you that there's carbon dioxide in a mixture.
No.
No, you need to already know what that is. You need to know the chemical reaction. So A is not right. The effect of changes in temperature on the rate of reaction. Nikita, what do you think about that?
I don't think it has. I mean, I think it has something to do with the rate of reaction.
What was the something that it had to do with the rate of reaction? We kind of went through this. What's the relationship between particle collision theory and Le Chatelier's principle? Particle collision theory explains Le Chatelier's principle. Le Chatelier's principle is just a prediction system. It has no explanation, right? Chemical systems do not care about partially counteracting changes. They're not sentient, they're not alive, they don't have a conscience, right? So if you want to ask yourself, well, why do systems partially counteract change? The explanation is in particle collision theory. So in summary, particle collision theory explains LCP. But is the converse true? Sid, does LCP explain particle collision theory and thus reaction rates?
Yes, it does.
I would say not really. It does talk about the shift of, the equilibrium shifting to the right, etc., shifting to the left, which is temporarily telling you what's happening to rates of reaction, but it doesn't necessarily explain those reaction rates. So what I'm going to put here is I'll put an asterisk. So question 9 is, B is a bit iffy, because what prediction can be made with LCP? The effect of changes in temperature and the rates of reaction? Okay, kind of, but it doesn't necessarily explain it, but it will tell you the direction the equilibrium shifts. It tells you about direction of equilibrium shifts, and it tells you about concentration as well. Good, what about C? The effect of catalysts on the position of equilibrium reactions. Does Le Chatelier's principle predict option C? Can anyone tell me, what does Le Chatelier's principle explain will happen when you add a catalyst to a system?
The rate of reaction just like increases.
The rate of which reaction? Forward and reverse, right? So if they increase equally, Nikita, does the equilibrium position change?
No, the constant doesn't change. Like the ratio of reactants to products doesn't change. It just reaches equilibrium faster.
Very good, right? So in summary, a catalyst does not affect the equilibrium position because it will increase the rate of forward and reverse reaction equally, right? So that is a prediction that can be made in the principle, right? So kind of like B, it is a prediction. Is it important in the chemical industry? Not really in terms of Le Chatelier's principle, right? So it's not answering the question too well. And what about option D? The effect of changes in concentration of chemical substances in equilibrium. What do we think about that? Sid?
Yeah, that's why I picked D, because Le Chatelier's principle determines like which concentrations increase and decrease.
Yeah. So I think 2001 question 9. This question is hard because it's so vague, right? Options B, C, and D are technically right. LCP does tell you the effect of changes in temperature on the equilibrium, but it doesn't in detail tell you how it affects the rate of reaction. It's in fact the inverse, where rates of reaction in particle collision theory explain Le Chatelier's principle. So that's my issue with option B. Option C, yes, Le Chatelier's principle does tell you how catalysts will affect the position of equilibrium systems, but it's not important in the chemical industry. We don't need to use LCP to explain that, right? And finally, D, I think D is the best answer because LCP does tell you the direct effect of changing concentration of substances on equilibriums. Literally what it does. So just in terms of wording, D is the best answer, but as you can see, B and C are also correct. They don't ask questions that are this vaguely worded anymore in HSC, so don't worry too much about that, but it's just to get you thinking. Now, moving on to question 2003, 30D, the Ostwald process, making nitric acid from ammonia. They've given you one step in the process. They've told you it's exothermic. So, Jacob, when it's exothermic, which direction are you going to add heat in? If you're going to add heat like actual reaction or product, are you going to add it on the right-hand side or left-hand side?
On the right-hand side.
Very good. So the way I think about this is, since it's an exothermic reaction, change in enthalpy is a negative value. If you want to bring it into a reaction, whenever you bring it in, you have to change its sign. So since it's negative heat here, to bring it into a reaction, you change its sign. If it was an endothermic reaction, you would have written it like this. You would have written positive heat, and when you bring it into this side of the reaction, it'll be negative heat. But that doesn't make sense. So then you have to bring it again to the other side of reaction. And so in an endothermic reaction, heat is like a reactant. In an exothermic reaction, heat is like a product. If you see heat and temperature like that, these LCP questions are very easy. So anyway, coming back to this, we're just going to write plus heat here. The reaction is exothermic, 2 methods to increase the yield of nitrogen dioxide. So actually, what are 2 things I could do to increase the yield or shift the reaction to the right-hand side?
decrease the concentration of oxygen.
This is where you have to kind of do stimulus opposite direction, right? If you decrease the concentration of oxygen, the system wants to increase the concentration of oxygen, and you're going to draw an arrow that points towards oxygen. You go to the left. Does that make sense, Akshita?
Yeah.
So the way I would be thinking about it is, again, applying the stimulus opposite direction. I want it to shift to the right-hand side. How can I cause it to shift to the right-hand side? I can take away heat. If I take away heat, I will want to increase heat, and so I will shift to the right. So decreasing temperature is one stimulus I could do. The other stimulus is I could take ammonia and I could remove it from the vessel, decreasing its concentration. The system will want to increase its concentration and thus shift to the right-hand side. Does that make sense to everyone? Good. What about pressure? What could I do to pressure to cause the system to shift to the right-hand side? Do I want to increase pressure or decrease pressure? Remember, I want it to shift to the right-hand side. Nikita, does the right-hand side have more or less gas moles?
It has less gas moles, so increasing the pressure, it will shift it to the right.
Very good, right? So we want to increase pressure. The opposite is decreasing pressure. There's 2 gas moles on the right-hand side. There's 3 gas moles on the left-hand side. So we'll shift to the right-hand side that way as well. Very good. So remember, we can't directly increase pressure, but what we can do is we can decrease volume of the vessel. We can shift all these gases into a smaller volume vessel. And usually in reaction systems, it'll be in a container where the lid of the container can move down through machinery to compress the gases. So you could say decrease in volume or an increase in pressure. Jacob, do you have a question?
Yeah, I was just gonna say, so because we want to increase the yield of the products, right? If we're removing products, wouldn't that actually decrease the yield, even though it's going to react to increase product?
I completely get what you're saying, but taking it out is not decreasing the amount that was produced. If 2 grams was made, 2 grams is made. If you take it out to be used, 2 grams is still made. It's just 1 gram was taken away. In fact, in most industrial reactions, Jacob, what we do is we'll have a pipe feeding the product out of the reaction system to shift the equilibrium to the right-hand side as much as possible. So that's often done in the Haber process. Any new ammonia that's made is compressed into a liquid and pushed out of the reaction vessel, and that will shift the reaction to the right. That doesn't decrease the yield because a certain amount of ammonia was still made. It's just taken out after it's made. So you don't have to subtract it from the amount that was produced. Does that make sense? Good, good. All right,
Wait,
good.
what about like in a closed system? You wouldn't be able to take that out.
That's true. In a closed system, you would not be able to take it out, but in industrial reactions, you can remove substances and you can add additional substances as well. So if they did say in a closed system, what would the changes you could make be? In a closed system, the changes you could make would be pressure volume changes, temperature changes, etc.
Okay.
Yeah, good, good. But I've never seen a question where they tell you it's a closed system and then what changes would you make. In the past 7 years, hasn't been a single question like that. So I wouldn't worry too much about the details there. Good. All right. What I'll get you all to do is take a 5-minute break and we will recap. And what we'll do is we will start touching upon the K constant. All right. So all of this will be homework, but we'll be touching upon the K constant for when you'll come back. So take a break till about 5:26, 27. Okay. So make sure you guys move around, get some water, take a bit of a break, and we'll come back. Okay, when we're all back, can we hit the raise hand icon? Back into things. Give us the final question. Good. Good. All right. Let's jump into it. So, here's question 10. You can all see the disturbances here. I'm just going to go across and ask each and every one of you, what were the disturbances? So, Anne, what was the disturbance at 2 minutes that you can see for this equilibrium system?
Would it be an increase in pressure or volume?
Would it be an
Pressure?
increase
In
volume?
pressure, but a decrease in volume?
Very good. Good. Right? More than often, it's the change in volume. It's very hard. It's hard to increase pressure directly, guys, because you have to add another gas that's inert, not part of the equilibrium. So usually what happens in real reaction systems is you will just decrease the dimensions of the reaction vessel, right? That's usually because the walls are being pushed by machinery and they can get larger or smaller. Akshita, what was the disturbance at time equals 5 minutes?
Was it pressure? A decrease in pressure?
So actually, look at the disturbance at 5 minutes, and again, break down the two phases. What are the two phases of change in concentration time?
Was it the initial stage and then the counteraction phase?
Good. What did we say about the counteraction phase? What does it obey?
Was it the stimulus? Like it would go opposite?
Yeah, and whose principle does it abide by?
The Chatelier's principle.
Very good, right? So we don't care about the Chatelier's principle part when we ask what the stimulus is, right? Look at the yellow part of this graph, the initial phase, and tell me, are all three things changing in concentration? Is only one substance suddenly changing?
Only one is?
Good.
The light
So you
blue.
straight away know it's not pressure, because all three should change in that yellow part of the graph, that stimulus phase. So what can you tell me now, Chita? What is the stimulus?
Concentration.
Good. What's happened? What's being increased or removed?
An increase in concentration.
Think about this, right? It started there, and it's now ended there. Is that going up or
down?
Exactly. So it's a decrease in concentration, in our case of COCl2. Okay, good. Any questions, everyone? Did everyone understand that? Good. All right. And finally, Jacob, what was the stimulus at time equals 8 minutes? Jacob, 8 minutes. What was the stimulus? Can't seem to hear you. I don't know if your mic is working. Nikita, 8 minutes. What happened at 8 minutes?
So I'm thinking like when you break bonds, you require energy, so temperature might have increased.
Good. It's just the cause and effect of that statement. I wouldn't link it to breaking bonds, releasing energy, etc.
Okay, but the temperature was changed, right?
Yes.
But I can't tell like if it's decreased or increased.
Good.
Wait, can you hear me now?
Yes, Jacob, I can hear you now. Yeah. It is hard to tell because you need to know the enthalpy, right?
Yeah.
I think I get what you're referring to in the sense that there's CO, there's Cl2, and you formed COCl2. And usually synthesis reactions are exothermic, right? Because synthesis requires successful collisions, which will release energy. So often heat will be here. Right?
Yeah.
And what we can see is that COCl2 has gone down, and these two have gone up. So the equilibrium has shifted this way, which is likely telling you that you increase temperature. The opposite is decreasing temperature. And you would have thus shift to the left-hand side for that. But that's a bit of a jump. It's definitely a logical conclusion, but no exam question will ever expect you to think to that level of detail. So all I wanted to hear was that the change or the stimulus is temperature, as there is no clear stimulus phase. Does that make sense? There is no sudden change of any of the reactants or products, that initial stimulus component of the concentration time graph. Sid, question?
What is the substance COCl2? Is it cobalt chloride or something else?
No, because cobalt chloride would be C lowercase o, right? It's a polyatomic, kind of polyatomic compound. The CO is carbon monoxide, and the COCl2, it has a name. Gotten the formal name of COCl2. I can find that out for you.
It's called phosgene.
So yeah, phosgene. There you go. That's right, phosgene. But you don't need to know that, right? It's just a combination of multiple different elements. Good. Jacob, question?
Yeah, I was gonna say, can't you just assume that it's exothermic because the bonds are being like formed, or they're being because it's gonna exchange heat?
You can, so like I said, you can kind of
release heat.
Assumption, but usually they'll always tell you. They'll never, as a student, you'll never be asked to make that assumption in an HC exam. But if it's forcing you to, there's no other way to do the question, then you can make that assumption. Okay?
Right.
But do you see how they help you out? In this case, for the actual question, they said at T equals 8 minutes, the temperature of the system was increased. And then you can go straight away, you can go, okay, well, the stimulus is an increase in temperature. The opposite is a decrease in temperature. I'll thus want to favor the endothermic reaction. And we went towards the left-hand side because cobalt, and not cobalt, carbon monoxide and chlorine increased, right? So therefore, I know the reverse reaction must be endothermic and the forward reaction is exothermic. But do you see how they gave you this little hint to help you answer the question conclusively, rather than guess synthesis is exothermic, breaking bonds requires energy, etc., etc.? Does that make sense, Jacob and Nikita? You definitely can apply that logic, but they'll never ever in an exam ask you to do that yourself.
Yeah, that makes sense.
Good, good. All right, let's go to the bulk of Mod 5, right? What you've learned so far, concentration time graphs is the highest yield component or question type of what we've learned till date. Now you're going to be learning about K. K is how we quantitatively measure equilibrium position, right? So let's actually read the inquiry question. Actually, could you just read out the inquiry question for us?
Deduce the equilibrium expression in terms of
As in the
K.
inquiry question, not the dot point.
Where's the was it?
Yeah.
Oh yeah. How can the position of equilibrium be described, and what does the equilibrium constant represent?
Good. So it's telling you two things. You need to know what the equilibrium position is, and then we'll talk about the equilibrium constant. So what does it mean when we say, let's say the A is forming B? What does it mean when I say the equilibrium position lies to the right-hand side? And what does it mean when I say the equilibrium position lies to the left-hand side? So, Zainul, do you want to explain to the class what does it mean when the equilibrium position lies to the left and then lies to the right? Take it away.
I think it's when equilibrium position lies to the left, it favors the reactants, and when it positions to the right, it favors the products.
What does it mean to favor the product or reactant? Because if we're favoring the reactant, Zainul, does that mean the reverse reaction is being favored?
No.
So then what does it mean to favor the reactant, favor the product? It's vague, right? And a lot of teachers reflect this vagueness when they're explaining this stuff. So I want us to understand it to a T. Sid, what does it mean when the equilibrium position lies to the right-hand side?
Meaning the reaction of the forward reaction rate is higher or greater than the reverse reaction rate.
I would say that is the biggest misconception students have about equilibrium position. So really good you brought that up, Sid, because I'm sure a lot of people would be thinking the same thing, right? But when they say equilibrium position, it doesn't make sense to say equilibrium position and then say the forward reaction rate is not equal to the reverse reaction, because equilibrium position implies the system is in equilibrium, and the very definition of equilibrium is forward reaction rate equals reverse reaction. Remember, I told you to imprint that into your minds. Whenever you use the word equilibrium, that is what it means. So let me tell you what it means when we say equilibrium position lies to the right, what it means when it lies to the left. When equilibrium position lies to the right, the first most important thing is, since it is an equilibrium position, the forward reaction rate is equal to the reverse reaction rate. But since it lies to the right, what it means is if I got the concentration of the product, which is on the right-hand side, and I divided it by the concentration of the reactant, which is on the left-hand side, if the equilibrium position lies to the right, this will be a very high value, aka there's much more product present and much less reactant present. Now, Jacob, going to you, what do you tell me about the concentration of reactants and products in equilibrium? Are they changing or are they constant?
They're constant.
Constant. So the value of B will not change. The value of A will not change. It's just that the concentration of B is constant and very high. Let's say 100 millimoles per liter. I'm just making it up. And A is very, very low, aka 1 millimoles per liter, 1 mole per liter, right? They're not going to change from those numbers. But as you can see, it is in equilibrium. That's the first point. And the position is actually describing the relative concentration of reactants and products. That is what the position is telling you. The relative concentration of product concentrations and reactant concentrations. Any questions? Free to ask away. So then, Nikita, what would it mean when equilibrium position lies to the left-hand side?
That means that there's more products. No, wait. There's more reactants.
Very good.
Because the equilibrium constant is higher.
Is lower. But we'll talk about equilibrium constant because I have not taught you about that, but you're completely right up to where we're learning, right? Which is, if it lies to the left-hand side, there is much more reactant present at a constant concentration, let's say 100 moles per liter, versus product, which is sitting at 1 mole per liter, much less. And what if there were equal concentration of reactants and products at equilibrium? In that case, you would say the equilibrium concentration or the equilibrium position lies towards the middle. Very good. Now, I've alluded to this quantitative way to measure equilibrium position. I said divide the products by the reactants, but it's not that simple. There's one little additional bit of detail we need to do if we want to quantify the position of equilibrium, right? And so if we're trying to quantitatively calculate how much is the equilibrium to the right, how much is it to the left, and how much is it to the middle, the formula is not just product concentrations. Remember, whenever I put a square brackets, it's concentration. That's what it means in chemistry, divided by reactant concentrations. What you'll notice is that it's the product of the product concentrations raised to the power of their stoichiometric ratio divided by the product of the reactant concentrations raised to the power of their stoichiometric ratios. Now, this will make a lot more sense when we go through exam questions. Okay, but for now, I want you to remember this formula, right? The equilibrium constant is a product of the products. So you multiply the concentrations of all products together. But for every single product concentration, you must raise it to the power of whatever numbers in front of it. So let's say that I had the Haber process. What would be the equilibrium constant for the Haber process? So I'll write it down to help you out. N2 plus 3H2 gives you 2NH3. Akshita, what is the equilibrium constant expression? So what is the product?
The ammonia.
Good. So you're going to write concentration of ammonia. And what numbers in front of ammonia?
2.
So you're going to raise it to the power of 2. And you're going to divide it by the reactants. Now, who are the reactants? N. Who are the reactants in the Haber process?
Nitrogen and Hydrogen.
Good. So what you're going to do is you're going to get nitrogen gas. You're going to multiply it by hydrogen gas, right? And then before you finalize that, you're going to raise them to the number in front of them. So, and what number's in front of nitrogen? What number's in front of hydrogen?
Nitrogen has 1, and then hydrogen has 3.
Good. So this is the expression for the equilibrium constant for the Haber process. And all you will now need to do is input their concentrations. Now, what are the units for concentration? What do we sub in? Let's go to Sid. What's the unit for concentration in all of chemistry, Sid?
Moles per liter.
Good. Moles per liter. Now, I just want to preface 2 additional things. K is unitless. If you get an answer for K, you're only going to write units, or you don't have to write anything for that matter. Now, the second thing for K, and they will love to ask you questions about this, because when you learn more and more content, you're going to forget this little bit of information that is so, so important. And it's that although 3 factors affect equilibrium, according to Le Chatelier's principle, only 1 factor affects equilibrium position, or K. I'm going to explain why that is soon, so don't worry about why just yet, but I want you to remember this. Equilibriums can be affected by temperature, pressure, volume, and concentration, but it is only temperature that affects the K constant. Pressure, volume, concentration have no effect. And they will test this indirectly multiple times, at least in your trial exams or at least in your HSC exam. So with a red pen, with a highlighter, I want you to highlight, circle, underline, write this. The 1 factor that affects K is temperature. We'll do 1 question, and then I want someone to remind me to explain why that is, or ask away after this 1 question. All right, I want you guys to tell me, what is the equilibrium expression for question 5? Or what is the K expression for 5? Good. When you get an answer, hit the raise hand icon. Get some water. Okay, good. Most of us got an answer. So let me ask Rithania, what's your answer for K?
So I got H2O on the top, and then it was times by Cr2 and O7 over CrO4 to the power of 2 and H to the power of 2.
Okay. Can you put your hand up if you agree with this answer? Hit the raise hand icon if you agree with the answer. Okay. Unfortunately, either I tricked you or you didn't remember that tiny detail about equilibrium and what doesn't and does affect it. And it also applies to K. I think it's good that we made the mistake, even though I did not stress you not to make it. Sid, what do we need to be cautious of with states when we're talking about disturbances to equilibriums?
Do they all have to be in the same state?
Not quite. They don't have to be the same state. I'll move on to Jacob. Jacob, what do I need to be cautious of in terms of state when I'm thinking about disturbances affecting equilibrium?
You don't include if it's a liquid or a solid.
Very good. And Jacob, can you explain why that is?
I think it's because the concentration of liquids and solids are pure. So
Constant.
yeah.
It's constant, right? And it's given 1, arbitrarily given 1. The reason is, guys, if I gave you pure gold, right? If I gave you 1 gram of gold, that's a constant concentration. Now, I can't increase the concentration of gold in pure gold. The only way I can do that is by giving you 2 grams of gold. And so when the number of moles increases, so does the volume of gold as well. The size increases of the pellets that I put in your hand. It has a constant concentration. The concentration of a solid is its density, and density is mass divided by volume. You cannot increase mass without increasing volume. So concentration of solids and liquids is 1. Now, you can include it like this, and you can just cross it out and write 1. You would still get the marks in an exam, but I would urge you not to even include it so you don't make that silly mistake, right? So I did not stress that when I taught you K, so completely understandable for those of you who didn't write that, but you now know you do not include solids and liquids in K. So that'd probably be my 3rd point about K, right? So remember, K is only affected by temperature. Do not include solids and liquids into K. And it's not just products divided by reactants. We raise it to the power of the stoichiometric ratio. Very good. You can do the rest of this question in your own time, but how about we do that in your own time as well. Okay, let me explain why I use this graph. Can anyone try explaining to me why is temperature the only factor that affects K? Nikita, give it a go.
Is it because, like, you know how, like, when you increase the temperature, it favors the endothermic reaction, right? So it shifts the equilibrium. So it kind of changes, like, the equilibrium constant is like, it's like a fraction, right? So won't it change, like, the ratio of reactants to products at equilibrium?
Pretty much got it, but I think the only thing we need to further elaborate upon is, well, how about for the other factors? But you're completely right? When you look at it, well, what is the equilibrium constant? It's just product concentrations divided by reactant concentrations, and then you do some tiny modification where you raise it to the power of the stoichiometric ratio. But in essence, everyone, the initial concentration of all these substances is here, right? Now, what's happening is they all change. This increases, and this decreases. So of course the concentrations all change. And in the same way, the K constant also changes. So let's just write the reaction so we can appreciate it, right? So in here we got CO plus CO2 gives me COCl2. What we see here is from the initial concentration, COCl2 has gone down, CO has gone up, Cl2 has gone up. The K constant is going to be equal to COCl2 divided by CO times Cl2. So from this, we know that the product has gone down and the reactant, CO and Cl, have gone up. It's a fraction, so this number, because its numerator has gone down, denominator has gone up, has decreased. Whereas if you look at all the other graphs, what you notice is that they also have an initial stimulus phase, unlike temperature. right? So what happens is, when you make a disturbance to a system, such as increasing all the concentrations of the substances, the system is shifting in such a way to preserve that equilibrium constant. And the same way with the second disturbance that you see here, see that sharp drop in the concentration of CoCl2. All the other concentrations change to restore that K value. But when you look at temperature, guys, the initial disturbance does not affect K. Do you see that? The initial disturbance did nothing to K. Unlike here, the initial disturbance completely disrupts K. Here, the initial disturbance completely disrupts K, as you see there. With temperature, the initial disturbance does not affect K. What affects K is the change due to Le Chatelier's principle. Whereas in the previous two examples, the change due to Le Chatelier's principle is restoring that K value. Okay, I've never again seen an exam question ask why, but the students that know why are the students that go on to get state ranks and first in New South Wales chemistry. It's because you dig deeper and you're more curious into the subject, right? But hopefully that makes sense to everyone. Good, very good. Let us move on to, I think this is quite important as well. Can you guys see questions? Let's do question 1A together, everyone. So this is the first question type you'll get for K constant question. This is not the most common question type, but it's one of the question types. I want you to pay attention to this. We're going to do question 1A together. Okay? So calculate the magnitude of the equilibrium constant for each of the following reactions at equilibrium. No, that's a bit too easy. You just have to sub that in, so that's not too bad. Let's do question 2. Okay. So they've told us the equilibrium constant for this reaction here at a particular temperature is 39. Why have they given us a temperature? Why have they done that, Sid?
Could you repeat the question?
Why have they told you that the K constant is 39 at 400 degrees? Why have they given you temperature for this question?
Because there will be a change in the KEQ value after the change.
Kind of. I asked you a bit of a hard question, but the simple answer was, what was the only factor that affects K, Sid?
Oh, temperature.
That's it, right? So every K value is temperature dependent. You cannot tell me what K is without telling me what temperature is, right? It's like telling me the weather without telling me what country we're in or city we're in, right? It makes no contextual sense. K is directly shaped and affected by temperature. So every time you guys get a K constant question, they'll always give you a temperature. And when they change temperature, you should come to the understanding that the K will also change. Good, right? So in this question, temperature has not changed, right? But something else has changed. We've gone from this equation here, and we've been told that the K is 39. So K equals 39. Now, and what is the K expression for the first equation here? K is equal to, what would you write as the expression?
It would be ammonia squared.
Good.
Over nitrogen.
Good.
Times hydrogen to the power of 3.
Very good, right? So we know that is equal to 39, and that's at 400 degrees Celsius. So that's for reaction 1, so I'm going to call that K1. Now, can everyone appreciate reaction 2, this is reaction 2, is exact same as reaction 1, but its stoichiometric ratio is different. Can we all appreciate that? Now, would that affect K or not? Sid?
Concentration would not affect.
Concentration would not, but since the stoichiometric ratio is now different, would that affect K?
Yes.
Good. You'll have to sub that in. Yeah, so the power to which things are is now going to change, right? So now for K2, Sid, what would be the expression for K2?
So it'll be ammonia at the top to the power of 8 over nitrogen to the power of 4 times hydrogen to the power of 12.
Okay. So with these kinds of questions, guys, where they give you one reaction and they give you another reaction, which is literally that same reaction or it's the reverse of that reaction, and they ask you for K, what you need to do, this kind of question has a title, it's a type of question. It's finding K2 in terms of K1. In terms of K1. Let's try understanding what that means. It means we need to get K2 and make it look like K1, or find the relationship between K1. Can anyone tell me, what do I need to do to K1 to get to K2? Sid?
Divide everything by 4.
Very close. Very close. But you made the silly mistake that I don't want you guys to make. Anne?
I was going to say times, or maybe to the power of 4.
Good. So the relationship is not just timesing it by 4, dividing it, right? It's changing the power of every single substance. What I mean by that is, if I cube root K2, right? Or if I get K1 and I raise everything by the power of 4, right? So if I go, okay, therefore K1 to the power of 4, what will that equal to? That would be equal to ammonia squared, nitrogen, hydrogen. I'm just writing K1 again. And then I'm raising everything to the power of 4. So all these powers get multiplied. Does that make sense? That will give me ammonia to the power of 8, nitrogen to the power of 4, and hydrogen to the power of 12. Does everyone agree? So therefore, I know K1 to the power of 4 is equal to K2. What's the value for K1, everyone? What number do we know K1 is?
39.
39. So what do we need to do to 39 to get K2?
Raise it to the power of 4.
There you go. We get 39 and raise it to the power of 4. What's our answer?
2, 3, 1, 3,
2, 1, 2, 1, 3, 4?
2, 3, 1, 3, 4, 4, 1.
2, 3, 1, 3. Okay, 2, 3, 1, 3, 4, 4, 1. I'm guessing that's what it is?
Yeah.
Okay, so now my question to all of you. Where does the equilibrium position lie for equation 1 versus equation 2? Which one has an equilibrium position that lies to the right, or lies more to the right? Nikita, I'll get you to...
K2.
Oh, Jacob? Give it a go.
No, I was going to say K2
Yeah,
has a greater
very
rise
clear.
to the right.
Exactly. K2 is such a huge number, which is telling you the concentration of products in this case, even though it's like raised to the power and there's slight differences, more or less you can say the concentration of products is, what is this, units, tens, hundreds, thousands, 10,000, 100,000, millions. This would be a good lottery win, but 2 million times greater than the reactant concentration, right? Rule of thumb. Very good. So when you're thinking about K, don't just think about it mathematically as numbers. When you look at K, think about where the equilibrium position lies. Is it to the right or to the left? So you understand what the K is telling you. Numbers tell you stories, right? That's what statistics, the entire field is. And you're just reaching the beginning or basics of that here. Very good. Good job. This is not a very common question type, but my tip to you guys is whenever they give you two reactions that are similar to one another, and they ask you to find the second K value, you'll need to find K2 in terms of K1. My other tip is, if you are not squaring, cubing, cube rooting, to the power of 4 rooting, you're doing something wrong. These questions never, ever involve multiplying by 2 or dividing by 2. If you're doing that, you know you've done the mistake. It will always involve cubing, squaring, raising to the power of something, or rooting to the power of something. Does that make sense to everyone? So those are my 2 tips for you. Okay? I'd like you to do question 1 yourself. Just tell me what the answer is. So hopefully you can see it, because I don't want you to get an answer, but good. Can you all see this question here? Reminder, we're going to 6:30, so because last lesson we finished at 5:30. But if any of you need to go, just let me know. That's also fine. Watch the recording, but I would recommend you all kick back, because the last 30 minutes I'm going to teach you probably the most important concept about K after this question. So give this question a go. Once you get an answer, let me know. All right, I'm going to get a quick snack while we're solving this. Who's got an answer?
Yep.
All right, so let's go with Jacob. What was your answer?
I got 0.142.
0.142. And Nikita, what about you? Nikita, what was your answer?
Yeah, I got 0.1418.
Good. Small thing though about significant figures. You want to have your answer in the lowest number of sig figs as the question, right? So this question, how many sig figs in this question, everyone?
3.
Good. So your answer should also be in 3 sig figs. Good. So all of you got the correct answer. Good. Good job. Any questions about these finding K2 in terms of K1? They're not too common, but when they come up, now you should be confident with approaching them. Okay. Good. What I'll get you to do now is solve these questions.
Do you have to add your valencies and states when writing those equations, or?
It's good to, yeah, because a substance, when the reactant or product, if it has a valency to its overall molecule, then it
Inside like the
brackets.
K equations.
Yes, I
Okay.
would include it. Okay, how about I give you a K constant question from an exam paper? Let's go CSSA 2022 paper. Let's see if we got a K question. So this is, there we go. This isn't too bad at all. But Anne, what's your answer for this question?
C.
Sorry, you're on mute.
Thank you, Rithania. I was just saying, the graphs that I showed you, they're definitely the most application-based parts of HSC Chemistry in general, and you only touch upon it in Module 8, which is applying chemical ideas. We're going to go all the way down to the bottom. I'm going to find you some K constant questions to do. This is testing your understanding of qualitative understanding of K. So what's our answer for question 3? I will get Zainul once you got an answer to tell me. Zainul, what are you thinking?
A.
Good. So you're just literally arranging it smallest to largest. That's quite literally it. More likely to reach completion when the equilibrium position lies to the right, because it's closer to the end. There are definitely a lot of calculation questions. We just got to find it.
Did we ever get a question they would give us the equilibrium constant, we would have to find the concentration of the substances?
Definitely. So I'm trying to
Okay.
find you a variety of different questions to do. Okay, let's do 2019 question 3 first, and then I'll find you some other K constant questions. So once you get an answer for question 3, 2019 CSSA, put your hand up. Very good. Already got some answers. Wait for one more person. Akshita, take me through question 3.
All right. So I think it was D.
Can you just explain it? Let me get Zainal. Agree, disagree?
I think it's C.
Titania?
I thought C.
Okay. Sid, can I get you to explain this question? What did you get?
So since the temperature was increased and gas B had also decreased, you can infer that the reverse reaction is endothermic.
Okay, let's break it down in a stepwise manner, right? We got stimulus opposite direction. We've been
Yeah.
told that the temperature increased. So the exact opposite of that is decreasing temperature, favoring the endothermic reaction. If B was decreased, which direction did we go?
To the left.
Good. So you know the left-hand side of the reverse reaction is endothermic. I did not think when I just explained this. I literally just followed the template that I've always been following. You don't need to think for these questions, guys. They're very, very easy once you always apply the same framework, right? So just like that, I know the reverse reaction is endothermic. The forward reaction must be
Exothermic.
exothermic, right? So straight I'm thinking, okay, forward reaction is exothermic. It's got to be A or D. What happened to K? What happened to K? You guys tell me.
So since it's products over reactants and B over A, so B has decreased, so then you can infer that the K has also decreased.
There you go. So my answer would have been A. Does that make sense to everyone? Right? So most of us would have got a different answer because we did not apply those same 3 questions. You might be wondering, well, how do I know when to apply it? Here's my tip. If it says LCP in the question and it's not a calculation K constant question, apply it. You can always apply it. Okay? Very good. Good job. Let me find you all a calculation question. Okay. This is a bit of a challenging question, but we will do it together. Okay. So I'd like you all to do question A and B and hit the raise hand icon, and I will go through question C with you. Bit of a challenge one, this question C. But it is a trial level exam, but we'll do it together. Okay? So hit the raise hand icon once you've got A and B down pat. Nikita, what's your reaction?
So it's carbon dioxide gas plus carbon tetrafluoride, so CF4, gives the CO carbonyl fluoride gas. I'm just balancing it.
Yep. Let's go to, has anyone balanced it already? Good, Anne, what's a balanced equation?
Is it just the 2 in front of the COF2?
Good, yeah, that's quite straight. Good job. Everything is gaseous. K is 0.5. So what does that tell you, Anne, when you see K equals 0.5? Is that telling you the equilibrium lies to the left, to the right?
to the left.
Very good. Anything less than 1 means the concentrations are not equal. So completely right. It lies to the left. Good. Write the equilibrium expression for the reaction, Zainal. What would it be?
So it would be K is equal to COF2 to the power of 2
Good.
over CO2 to the
Yep.
power of 1
Good.
times the concentration of CF4 to the
Good.
power of 1.
Good. Perfect. So that's our reaction. Just make sure to check the states, all right? Gaseous, you definitely can include it in K. Now, this question, I want you guys to read this question first. I don't expect you to know at all how to approach it, okay? Just read it for me and just understand what's happening. We add some gases together. They're allowed to mix. We give it some time, and it forms an equilibrium. And then we need to find, this is an even harder question. Maybe what I'll do is I will give you, this is a much better question. Okay. So I just want you to imagine this is part C of the question, right? You've done A and B, you've written the equation, you've got the constant expression. This is a much better starting question for us to do. Have a read of it first. I'll give you about 30 seconds. Understand what's going on. And then, once I show you this question, you guys have gone through 50% of Mod 5. So the only other thing we have left is KSV, common ion effect. A few more question types of this, and you'll finish Mod 5. Mod 5 chemistry is not that long. Good. And question?
Are we looking at question 8 or 9?
8. Question 8. Have a read. I'll give you about 30 seconds, and then we'll do it together. Are any of us interested in the finance world? So I'm talking like investment banking, talking like working at the banks. Because what happens is majority of students go into the commerce. When we go into the commerce, you work at PwC, you'll be working at the big four. So PwC, Deloitte, I've forgotten other companies, but those are like, that's the main pathway for selective school student university graduates when you look at the statistics. Anyone interested in that?
Yeah, sort of.
Yeah, so it's an interesting field, and what I would encourage you to research into, Jacob, is also look into consulting, and I'd want all of you to look into it, because what happens is every year 2 or 3 medical students will graduate, and instead of joining the traditional doctor workflow, they'll go and join a company that does consulting. Consulting is pretty much problem solving for other people, right? That's what consulting is. So as a doctor, you can be hired by the government and solve problems for public health, policy making, etc., right? Medicare, what tax rate should Medicare be, modeling the returns, where should Medicare be distributed. The government doesn't do this stuff. They outsource it to private companies that do it and do the consulting, the problem solving, and then fix the problem. The government implements it. That's what the government does for everything. So for a lot of you, I would highly recommend, if you like problem solving, working with a team outside of the traditional pathway, go into consulting. It's a really, and lucrative wise, income wise, you make definitely more than a doctor in the first couple of years, and most of them will go on to make more than a doctor in their lifetime as well. So I think consulting from a financial security point of view, from a work point of view, is a very interesting line of work to go into. Nikita, question?
Oh no, I just got the answer.
Oh, good, nice. So you've got the answer, Nikita.
Right.
What was your approach? Did you create a specific kind of table?
Yeah, I made a rice table.
Very good, very good. So that's what I'm about to teach us now. Okay. So what I wanted you all to understand is, reading this question, you've been told initially means time equals 0. Right? So exactly at time equals to 0, the second this gas is placed in the vessel, that's the initial point in time, right? What happened is, after time equals to 0, an equilibrium was achieved. So time equals to 0, some period of time went by, and then we reached the time of equilibrium. And when we reached time of equilibrium, we were given data about some of the products or reactants. So I want you guys to really appreciate and understand this, right? At time equals to 0, we're given data about some of the reactants or products, and then at time equals equilibrium, we're given data about some of the reactants or products. Whenever you are given any moles or concentrations of any reactants or products at different time points, your head should immediately be thinking RICE. RICE is an acronym. We're going to go through that now. Okay, but in summary, in future, any time you're asked a question about K and you're given concentration at time equals to 0 and then concentrations of moles at time equals equilibrium, you'll be applying a RICE table. A lot of students, even before the HSC, don't know when to use this table, so that is when to apply it. We'll do more questions as we go. So RICE stands for, R stands for the ratio. I stands for the initial concentration, so I'm going to annotate it for you. What is the stoichiometric ratio? What is the initial concentration? What is the change in concentration? And E is what is the equilibrium concentration? And that's what we're going to fill out together. Okay, so we've got this reaction where we've got PCl5 forms an equilibrium with PCl3 plus Cl2. And what is the ratio of all of these gases?
Is it 1 to 1 to 1?
Yes, I'm sure 1 to 1 to 1. I'm just going to draw a line here to separate all the substances, right? And just note that this is a reactant on the left-hand side, and the two things on the right-hand side are products, the two substances. What have we been given? Initially, there is 0.2 moles of phosphorus pentachloride. Now, this is where we're going to start doing calculation questions. What is 0.2 moles, Zainul? Is it a concentration, a number of moles, a mass? What is this?
Number of moles.
Good. So you guys are going to start learning how I break down calculation questions. What I write is, if it's number of moles, I write little n, and then I write the substance. So phosphorus pentachloride, and then I write equals to 0.2. That's the initial. So number of moles initially of phosphorus pentachloride is 0.2 moles. That's my data. Okay. What have we been given? It's in a 2-liter vessel. So I'm going to write V, or volume, is equal to 2 liters. And so equilibrium could be achieved. Data was collected, and then at equilibrium, it was found that there's 0.15 moles of chlorine gas. So now I know the number of moles of chlorine gas at equilibrium is equal to 0.15 moles per liter. Sorry, moles, because that's what number of moles is. What's the volume, Jacob?
2.
Very good. So Jacob, you've been given number of moles of 2 different gases, and you've been given a volume. If you have N and you have V, what can you find?
I can find the concentration.
Very good. And remember, in a RICE table, guys, the only value you're inputting is concentration. It is wrong to input number of moles, wrong to input mass. The only thing that works is concentration in moles per liter. So we're going to now apply that. So what is the concentration initially of phosphorus pentachloride? What's 0.2 divided by 2? 0.1. Does everyone agree? Right? So what you're going to write is initial concentration of PCl is 0.1. Now, what is the initial, or what is the equilibrium concentration of chlorine gas? Same thing, we write N on V. What's the N value? 0.15. What's the volume? 2. What's our answer for that?
0.075.
Very good. Now, what was the initial concentration of phosphorus trichloride and chlorine gas, Ritanya? Because you need to visualize this. Initially, 0.2 moles of phosphorus pentachloride was put in a vessel. So in a 2-liter vessel, there is only 0.2 moles of phosphorus pentachloride. Ritanya, is there any phosphorus trichloride, or is there any chlorine gas?
No, it's going to be 0.
Very good. Now, Ritanya, I know the initial concentration of chloride. I know the equilibrium concentration of chloride. What was the change in concentration of chloride, Ritanya?
0.075.
Good, it increased by 0.075. Now, how many parts in this cooking recipe was chlorine? Again, back to you, Rithania. What number was in front of chlorine in the stoichiometric ratio?
1.
1. So now we know 1 part is equal to a change in concentration of 0.075. Now, what's going to happen to phosphorus trichloride, Nikita? It's a product as well. Will it increase like its other product, or will it decrease?
It will increase because it's a product by the same amount.
Exactly, because there's the same number in front of it in our stoichiometric ratio. If it was 2 here instead of 1, Nikita, what would phosphorus trichloride increase by?
0.15.
Very good, right? So 2 parts. Perfect, right? So now we know that the equilibrium concentration of phosphorus trichloride is also 0.075. And finally, your phosphorus pentachloride decreases by that amount, right? Because it's a reactant. So unlike the products, it decreases, and it's also 1 part in our cooking recipe. Does anyone know if it was 3 in front of a phosphorus pentachloride in this question, how much would it decrease by?
0.225.
Yeah, which is more than the initial concept. That doesn't make sense, but as long as you understand the ratio, I'm happy.
Yeah.
Very good. So this is going to be 0.025. Good. So remember, when you're using K, you only sub in the equilibrium concentrations because K is an equilibrium value. So now what we're going to do, everyone, is we're going to find the expression for K. And what is the expression for K for this equation?
For this equation, it is PCl, yeah, that over PCl to the to 5, like the.
Good. And now, when we sub that in, Nikita, what do we get as our answer?
0.225.
Nailed it. And what's the unit, Nikita?
There's no units.
Very good. So the answer is A. And so that leaves us with how to do rice tables. Now, I know this is a bit of a rushed question because we're running out of time for today. So we finished today's class, but what I'd highly encourage you all to do is when you get your booklet is going to come with all these additional questions, right? So this is about 60 pages of trial questions I've collated for Module 5. If you can do these questions as you're learning the content, you're set. And for those of you asking where the solutions are, I'm going to put every single paper up in the Google Drive and give you access to it. So don't worry about that for now. I just want you to start doing the questions. Okay. And the other thing, for those of you who are new to us, homework is also, as we go through the booklet, any questions we skip, like all of these questions that we just skipped, I'd expect you to also do that for homework for the next lesson as well. Okay. Remember, the time I'll check this is before you sit your exams. Right? I'd want to see a completed booklet, and I'd also want to see the completed additional questions for that module. But does anyone have any questions from what we learned today? Good, you're all doing really well. I would just say the only thing to focus on is decide how you want to play this game, right? You can either choose to write notes yourself, right, from scratch. You could do that if you like, or you could just use my notes. But if you're going to use my notes, you need to guarantee to yourself that you're going to be doing more past papers with the additional time that you save. Because unless you do that, you will not benefit in HSC Chem. Chem, bio, all the sciences, guys, is just solely who does the most past papers, who does not repeat the same mistakes again. That is all chemistry and biology are. And even more for maths, I would say. Okay, good. All right, if you have no further questions, I will see you all next week. And if anyone has any questions, you can stay back after class. And Nikita, could I get you to stay back after class? Thank you.
Yeah.
Cool.
Thank you.
See you guys. Bye, Akshita. Bye, Tanya.
Thank you.
Yeah.
Bye,
Thank you.
Jacob. Bye, Sid. Bye, Zainal. Sid, question?
Yeah. Since like my assessment has a lot of mod 6 in it, is it possible for me to get access to that?
Sure. I'll give you Google Drive access to Mod 6 HSC Chem. Sure. What's your exam?
Oh yeah, so it's a Pratt processing, so it's on Arrhenius theory, Brodson-Lowry theory, and like modeling acids and bases, as well as solubility rules, and toxic cycad fruits.
It's a bit of mod 5, a bit of mod 6, right?
Yeah.
Okay, sure. What I would encourage you to do, can you bring notes into class?
Yes. You have like a sheet of notes, a prac report, and a table.
So feel free to send that across to me. The only thing I will say is whenever it's a task where you can bring in your notes, you're going to have much less time for the questions. And that's how they make the exam structured to keep it challenging. So I would say you should already know every single bit of information on the notes that you bring, and that should just be a peace of mind, a security thing, right? I would make sure that I do every single relevant question for mod 5, toxins and cycads, and mod 6 with the Ka, Bronsted-Lowry theory. Questions shouldn't be too hard. The things I'm going to tell you to revise the pros and cons of Bronsted-Lowry theory. I'd want you to also research Lewis theory, the ammonia dilemma, and on top of that, just be ready to do pH. Do you need to know titration set or not for the first assessment task?
Not for this one.
Okay, so also know how to do basic pH calculations, and then know the experiments for acids and bases in mod 6, which is going to be your cycacin, sorry, not your cycacin, your anthocyanin, your red cabbage indicator, differentiating common household, acids and bases, etc. Okay.
Yeah, I'm just a bit confused on the Lewis theory. That was the only one that I'm confused about. But yeah.
Okay, we can talk about Lewis theory. Do you know Bronsted-Lowry?
Yes, most of it, yeah, I do.
Okay, give me 1 minute. I'll just respond to the others, and maybe in 2 minutes so I can quickly explain Lewis theory. And any questions?
Mine was just about like medicine, like getting into medicine. And also I got my chemistry assessment task. We have to model an equilibrium and then it's like a presentation on that. And they've got questions and stuff. And then the last part of the assessment is that we have to write our own exam question, write a criteria and like a sample response.
So what I'd recommend is this week you think about what your model of equilibrium is going to look like. Think about the pros and cons of that model, which you'll be including in your report or presentation, because that's probably usually what they'll ask you, limitations of the model, etc. Various models that people like to use include like waters in cylinder, water volumes in cylinder, and you can use pigmented, you can add pigment to the water. Other equilibriums you can use. There's so many models on the internet. So let's just search equilibrium model and you'll find a lot of different models to represent chemical equilibrium.
Yeah.
Pick one. Let me know what you're picking and I'll let you know, give you the green light, and then you can write up your report and the questions, send it to me and I'll have a look at it. Okay.
I was looking at the water one, but one of the parts is like we have to talk, like explain the forward reaction and stuff. How would I explain like the forward reaction for water going back and forth?
I wouldn't pick the water one. It's too simple, right? So I would pick something else. If you can use like digital software and you can create like particle collisions, that's also an interesting model you can do. But try not to use a very simple or basic model because that will cost you a lot of marks. So think of another model, find another one and send it to me. Then we'll talk about that. Just very quickly, Nikita, did you have a question?
No, not really.
Okay, yeah, I just wanted you to stay back to, first of all, just talk about notes and such. And I guess you can send me a message on class about whether you'd like the resources and next lesson and such. How does that sound?
What do you mean on class? Like, you want
Sorry?
me to, like, do you want me to, like, what do you want me to do?
Just message me if you're happy to continue for the term or whether you wanted, resources, X, Y, Z.
Okay, yeah. Okay.
All right, cool.
Oh, I had one question. Sorry.
Yes.
So like the graphs that you were giving us, right?
Mm.
In regards, I don't know if you've done this like in previous class, but did you do like the rate graphs?
We have gone through rate graphs, so you can get access to the recordings and watch the rate graph lessons.
Okay. All right.
Cool. All right. Bye, Nikita.
Bye.
And for your question, sorry, could you repeat the part where we'd left off? So we're talking about models.
Yeah, and then it was just about like getting into medicine.
Okay. What did you want to know about getting into medicine? Because there's a lot to it.
Yeah, there's a lot. It's kind of freaking me out how how well you have to do with everything.
So my advice is medicine's a good career. It's a lot of hard work, even after medical school, especially when you like medical school itself is not that hard, I'll be honest with you. Getting in is hard. And then it becomes hard in the final couple of years, because it's a lot of exams. And then it's hard after, and I wish someone told me about this, but it's hard to become a specialist doctor once you've graduated as well. It's very competitive to become a surgeon, a neurosurgeon. To give you perspective, there's only one neurosurgeon position every year, and there's hundreds of really smart doctors going for it. So just understand that the lifestyle, especially if you want to do something like surgeries, is intense. But there's, of course, like GP, psychiatry, all those much more relaxed lifestyles as well. With getting into medical school, I would say get the Medify question bank, start doing UCAT questions, treat it like 2 units, and aim for every single medical school. So worst case, have JCU, which is in, I think, Queensland, Townsville, as your like worst case option. But honestly, it's not even like, it doesn't matter which medical school you go to. You'll graduate a doctor, and it does not affect your employability at all. In fact, a lot of my friends who went to JCU said it was one of the best times of their life, because they moved out of home, they made so many friends, they stayed on campus. Whereas UNSW, all of us just stay at home for majority of the degree. So key tip is apply everywhere if you are serious about getting into medicine, and treat UCAT like 2 units.
So would you recommend preparing for it like every day, or like sometime throughout the week or something?
Literally how you'd prepare for a 2-unit subject. So you wouldn't study every subject every single day, right? So I would say maybe once or twice a week, spend, up to three hours, maybe 4 per week, maybe 3 hours in the first couple of months, and then go up to 4 or 5 even in the weeks leading up to the UCAT.
So
okay? All depends on your Medify marks.
Oh, did you get in through like the UCAT and the ATAR, or did you do it the other way?
I graduated a long time ago. We didn't have the UCAT. We had a 3-hour version of that was written, called the UMAT, which was an absolute horror to sit. So I'm glad they've scrapped that since. But yeah, I got in right after high school. Doesn't really matter though. A lot of people get in first year university, second year university. Some of my friends do GAMSAT and get in. It does not matter too much. It's just about how many years are you willing to try if you do not get it the first go, because it is continued hard work, right? Yeah.
Thank you.
No worries.
All right,
Sid.
Bye.
Very quickly, I'll talk to you about electron Lewis theory. So Sid, tell me about Bronsted-Lowry theory.
So what I've researched so far about it is that it involves acids being proton donors, like giving protons to the base, while the bases accept